There are different types of non-stationarity, and on this slide I've mentioned 3 of them: stochastic non-stationarity, deterministic non-stationarity, and a mixture of 2. So we have already started discussing the stochastic non-stationarity, therefore let's continue discussing it. And when it comes to stochastic non-stationarity, there are 2 possibilities. A process can be a random walk without drift, and an example of such a random walk without drift could be the following equation. So we see that some variable y is a function of its own value in the previous period plus the error term. And if you look at the coefficient next to yt minus 1, you will see that the coefficient is 1. And from this equation, we can write the following equation. So if instead of t we substitute the value of 1, we get that y1 is equal to 1 minus 1, which is y0, plus the error term 1. If we would like to get the equation for the second y, so instead of t we substitute 2, and we get y2 is equal to y1 plus the error term. And we have the equation for y1. Here it is, y0 plus u1. So instead of y1, we substitute y0 plus u1, and we get y0 plus u1 plus u2. We can do the same for the third period. So y in the third period is equal to 3 minus 1, so y2 plus the third error term. We have the equation for y2, right? It's y0 plus u1 plus u2. So let's substitute it into this equation, and we get y0 plus u1 plus u2 plus u3. And this whole system of equations can be shortly written as y in period time is equal to its value in the previous period plus the sum of the error terms, like u1 plus u2 plus u3 and all the way to un. So what this term over here, the sum of the error terms, actually has its own name, and it's called stochastic trend. And it represents the fact that random shocks are persistent in the system, or in other words, shocks do not die away. So whenever a shock happens to the variable y, it stays in its equation, so within this sum of the error terms. And because of this, we say that the model has infinite memory. So every shock that happens to y stays in the system, and it stays in this sum term. Another example of stochastic non-stationary process is a random walk with drift. Let's have a look at the example of such a process. So yt is now a function of beta 1, so the constant term, plus its own value with the previous period, in the previous period, coming with the coefficient of 1 and ut. This equation can be rewritten in the following way. So let's, for example, get the value of y in the first period. So we substitute 1 instead of t, and we get that y1 is equal to the constant plus y0 plus u1, right? So 1 minus 1 is 0. If we want to get the value of y in the second period, we substitute the value of 2 into the equation. So we get beta 1 plus 2 minus 1, which is 1, so y1 plus u2. And we have the equation for y1, here it is. So let's substitute it into the equation, and we get beta 1 plus y0 plus u1 plus u2. If we would like to get the equation for the third period, we follow the same procedure. So y in the third period will be equal to beta 1 plus y3 minus 1, which is y2 plus u3. And once again, we have the equation for y2. Let's substitute it into the equation. We get beta 1 plus beta 1 plus beta 1 plus y0 plus u1 plus u2 and plus u3. And this system of equations can be shortly written in the following ways. So y in period t is equal to its own value in the previous period plus the sum of the constant terms plus the sum of the error terms. So we get that the random walk with drift has now two trends. It has stochastic trend, the same as the one from the model of the random walk without drift, and we've also got another trend where beta 1 is a drift parameter. So once again, in this model, the shocks do not die away, they stay in the system, they are persistent, so we say that the model has infinite memory, and we also have a drift, so the constant value.